Picture this. It's 1973, and a beat-up International Harvester Scout pulls up to the starting line at Pikes Peak. The other racers are laughing. They're running purpose-built racing engines, high-strung power plants, built for one thing: speed. Meanwhile, this Scout is running what's essentially a tractor motor. The same engine that powered combines harvesting wheat in Kansas. The same power plant pulling plows through Iowa mud. When that Scout crossed the finish line, nobody was laughing anymore. It had just set a class record that would stand for years. This is the story of how International Harvester's agricultural engines became unlikely racing legends by doing exactly what they were designed to do: deliver relentless, unwavering torque hour after hour, mile after mile, when everyone else's engines were gasping for air. And let me take you back to 1961, when International Harvester engineers faced a problem. Farmers were demanding more powerful tractors, but they needed something racing engine builders never worried about: the ability to run at full load for 16 hours straight in 100-degree heat. No pit stops, no cool-down laps, just constant brutal work from dawn to dusk. The solution they developed would accidentally create one of the most underestimated competition engines in American motorsport history. An International Harvester wasn't trying to build a race engine, they were the antithesis of sexy. While Ford and Chrysler were locked in horsepower wars, IH engineers in Fort Wayne, Indiana, were obsessing over something completely different: the torque curve. Not peak torque, not maximum horsepower, the shape of the torque curve itself. See, a tractor engine faces a unique challenge. When a plow hits a rock or dense clay, the engine can't stall. It needs to automatically develop more torque without the operator touching anything. This characteristic, called wheel lugging ability in agricultural circles, meant IH engines needed torque curves that actually increased as RPM dropped. Most engines produce peak torque at a specific RPM and fall off on either side. IH engines were designed to pull harder the more they bogged down. The 345 cubic inch V8 that debuted in 1961 was the first manifestation of this philosophy in a light-duty engine. On paper, it looked pathetic next to contemporary performance engines. While a Chevrolet 327 was making 375 horsepower, the IH 345 produced just 197. But here's where it gets interesting. And that Chevy made its power at 6,200 RPM. The IH 345 made its peak at 3,800 RPM. More importantly, it made 90% of its peak torque from 1,200 RPM all the way to 3,500 RPM. That's a 2,300 RPM spread of near maximum torque. The Chevy's torque band, where it made 90% or more, about 800 RPM to once and in. The engineering that created this unprecedented torque spread was deceptively sophisticated. IH used what they called wage-controlled turbulence combustion chambers. The intake valves were shrouded on one side, creating a swirl effect as air entered the cylinder. This swirl persisted through the compression stroke, improving fuel mixture and allowing complete combustion even at very low RPMs where most engines struggle. The cam profile was unlike anything in Detroit. Where performance cams used radical lift and duration to maximize high RPM breathing, IH used what they called a torque grind: moderate lift, short duration, and, critically, very gentle ramps. This meant the valves opened and closed gradually, maintaining cylinder pressure at low speeds while reducing valve train stress. But the real secret was in the bottom end. IH engines used massive bearing surfaces. The main bearings were 3.125 inches in diameter compared to 2.5 inches in most V8s. The connecting rods were forged steel I-beams thick enough to use as pry bars. The crankshaft was forged from 1053 steel and weighed 78 pounds, 20 pounds heavier than a big block Chevy crank. This overbuilding served a purpose beyond durability. The massive rotating assembly created tremendous flywheel effect. Once spinning, it wanted to keep spinning. This rotational inertia smoothed out power pulses and maintained momentum through load changes, exactly what you needed when a plow suddenly hit harder soil. In 1965, an unlikely racing application emerged. The Baja 1000 had just started, and it presented a unique challenge. Unlike circuit racing, where engines operated in a narrow RPM band, or drag racing's 10-second blasts, the Baja required engines to survive 1,000 miles of the most punishing terrain on Earth. Temperatures soared to 120 degrees, dust clogged air filters, rocks launched vehicles airborne, engines had to survive it all while running flat out for 20-plus hours. A privateer team from Phoenix decided to enter an international scout. They didn't have the budget for a racing engine, so they ran what they had. A stock 304 cubic inch IH V8 making 193 horsepower. The competition laughed. Factory-backed Ford Broncos were running 289 high-po engines. Chevrolet-powered buggies had 327s. The Scout was bringing a knife to a gunfight. Yet, 27 hours later, that Scout crossed the finish line, third overall, first in class. Most of the high-strung racing engines had expired in the desert heat. The Ford Hypos had overheated. The Chevy small blocks had scattered connecting rods. The IH-304 hadn't even consumed any oil N-word spread through the off-road racing community. These tractor engines were virtually indestructible. But it wasn't just durability. Drivers discovered something else in the desert. The IH's torque curve was perfectly suited to off-road racing. In sand, wheel speed is everything. Too little and you bog down. Too much and you dig in. Racing engines with peaky torque curves required constant shifting and throttle modulation. The IH engines just churned through it, drop it in third gear, and leave it there for 50 miles. The broad torque curve meant the engine pulled itself out of bogs that would stall other engines. And then by 1968, International Harvester noticed racers were buying their engines. They decided to create something special, the 392 cubic inch V8. This wasn't just a bored and stroked 345. It was a clean sheet design incorporating everything IH had learned about making torque. The bore was 4.25 inches. The stroke was 3.656 inches. That's under square. The stroke is shorter than the bore diameter, which typically favors high RPM operation. But IH's combustion chamber design turned conventional wisdom on its head. The controlled turbulence chambers worked better with the larger bore, creating an even more homogeneous mixture. Einstein, the 392, produced 235 horsepower at 3,600 RPM and 405 lb-ft of torque at 2,000 RPM. Again, the numbers looked pathetic compared to performance engines. A 396 Chevrolet Big Block made 425 horsepower. But look at the torque curves dotted under on the Chevy 396, made peak torque of 415 lb-ft at 3,200 RPM. At 2,000 RPM, it made about 340 lb-ft. At 1,500 RPM, maybe 280 lb-ft. The IH 392 made 405 lb-ft at 2,000 RPM, 395 lb-ft at 1,500 RPM, and still pulled 350 lb-ft at 1,200 RPM. It was making more torque at idle than most engines made at 2,000 RPM. The internal components were agricultural grade. Connecting rods were forged 4340 steel, shot-peened, and magna-fluxed. Each rod weighed 928 grams. NASCAR Sprint Cup rods weigh about 600 grams. The pistons were cast aluminum with steel inserts at the ringlands. They weighed 740 grams each. For comparison, a racing piston might weigh 400 grams. This mass wasn't inefficiency. It was thermal management. The heavy pistons absorbed and dissipated heat better than lightweight racing pistons. The thick cylinder walls, 0.375 inches compared to 0.225 in most V8s, acted as heat sinks. The massive coolant passages could flow 90 gallons per minute, compared to 50 gallons in typical V8s. In 1971, Bill Strop, a legendary off-road racer and Ford factory team manager, defected to International Harvester. Ford had pulled out of off-road racing, and Strop saw potential in IH's engines. He convinced International to secretly support a racing program, and Strop's first move was genius. Instead of trying to make the IH engines rev higher or make more peak power, he optimized them to do what they already did best: make torque. He worked with IH engineers to develop what became known as the Strop Power Package. The package included a special camshaft that actually reduced peak horsepower from 235 to 220, but it increased torque below 2,500 RPM by 15%. The intake manifold was redesigned with smaller runners that increased velocity at low RPM. The carburetor was downsized from 650 CFM to 500 CFM, again sacrificing top-end power for low-speed response. The result was an engine that made 440 lb-ft at 1,800 RPM. It would pull from 500 RPM to redline at 4,000 RPM without a stumble. In an era when racing engines needed 3,000 RPM just to clean out, the Strop-tuned 392s would accelerate smoothly from idle. The 1973 Pikes Peak International Hill Climb became the proving ground. Pikes Peak is unique among racing venues. The 1242-mile course climbs 4,620 feet, starting at 9,390 feet elevation and finishing at 14,110 feet. At the summit, naturally aspirated engines lose 40% of their power due to thin air. But here's the thing about torque. It doesn't disappear with altitude as dramatically as horsepower does. An engine making 400 horsepower at sea level might make 240 horsepower at 14,000 feet. But if it made 400 lb-ft at sea level, it still makes 320 lb-ft at altitude. The percentage loss is less for torque than horsepower. Than the IH engines, with their massive torque reserves, maintained pulling power where high-revving engines wheezed. A Chevy 350 that made peak power at 5,500 RPM at sea level could barely reach 4,000 RPM at the summit. The IH engines with peak power at 3,600 RPM could still reach redline even in the thin air. Jerry Ball entered a Scout II with a Stroppy-prepared 392. His competition included purpose-built hill climb specials with aluminum bodies and racing engines. The Scout weighed 4,200 pounds. It had the aerodynamics of a barn. Vegas odds had it finishing dead last if it finished at all. Ball's strategy was simple. While others rocketed off the line, he maintained a steady 3,000 RPM. The IH engine settled into its sweet spot, churning out constant torque. As the course climbed and the air thinned, the racing engines began to struggle. Drivers were downshifting frantically, trying to keep their engines in the power band. Ball never shifted. Third gear, 3,000 RPM, mile after mile. The engine temperature never exceeded 190 degrees. Oil pressure never dropped below 45 psi. As others stopped to cool overheating engines, Ball churned past. At the Devil's Playground, a section at 13,000 feet, a Porsche 911 with a racing engine was stuck in first gear, the engine screaming at 7,000 RPM, but barely making enough power to maintain speed. Ball passed him at 2,800 RPM in third, the IH engine pulling like it was at sea level. He crossed the finish line with a time of 13 minutes, 26 seconds. It was a class record. More incredibly, his average speed was higher in the thin air sections than the lower portions. While others slowed as they climbed, Ball maintained constant velocity. The engine's temperature at the summit? 185 degrees. It could have run another 20 passes. The racing world took notice. Here was an engine that violated every principle of racing engine design, yet dominated in specific conditions. It was too heavy. It didn't rev high enough. It made pathetic peak horsepower. But it just kept pulling. In 1974, the Score Off-Road Racing Series introduced a new class, Class 4, for full-size 4x4 vehicles. It was designed to attract weekend warriors who wanted to race their daily drivers. What it actually did was create a showcase for IH engines, and the rules were simple. Stock chassis, stock suspension mounting points, and engines no more than 0.060 inches over bore, no aftermarket blocks, no racing heads. This played directly into IH's strengths. While others were limited to factory performance parts, IH's factory engines were already overbuilt. In the 1974 Baja 500 saw 7 IH-powered vehicles at the start. Factory teams from Ford and Chevrolet brought specially prepared race trucks. The IH entries were mostly privateers running engines built in their garages. And 500 miles later, IH-powered vehicles finished first, second, third, and fifth in Class 4. The factory Ford F-250 with a 460 big block expired at mile 280 with a ventilated block. The Chevy K5 Blazer with a 454 dropped a valve at mile 360. Every IH engine that started finished but it was the telemetry data that really told the story. The winning Scout, driven by John Crean, never exceeded 3,500 RPM for the entire race. His average engine speed, 2,750 RPM. The Ford that expired? It averaged 4,800 RPM before the engine let go. The IH engine wasn't working hard. It was loafing along at the same speeds it would pull a combine. Andern International Harvester's engineers, watching their agricultural engines dominate racing, decided to study why. They instrumented a 392 engine with dozens of sensors and ran it on a dynamometer programmed to simulate the Baja 500. What they discovered challenged conventional racing wisdom. The engine's combustion efficiency at 2,500 RPM was 34%. That's the percentage of fuel energy converted to mechanical work. A typical racing engine at 6,000 RPM achieved about 28% efficiency. The IH engine was extracting more energy from every gallon of fuel. Over 500 miles, that meant using 20% less fuel while making the same average power. The thick cylinder walls and heavy pistons they discovered created a phenomenon called aerothermal inertia. Racing engines with thin, lightweight components quickly matched coolant temperature. When coolant got hot, so did the combustion chambers, promoting detonation. The IH engine's massive components absorbed heat spikes, maintaining stable combustion chamber temperatures even when coolant temps rose. The broad torque curve had another unexpected benefit: gear multiplication. In any given gear, the IH engines operated over a wider speed range. A racing engine might need to shift from second to third at 30 mph to stay in its power band. The IH engine could pull third from 15 mph to 60 mph. Fewer shifts meant less time with the clutch disengaged, more time applying power to the ground. And by 1975, other manufacturers were studying IH's approach. Ford developed the 460 Ruris Police Interceptor with a mild cam and improved low-end torque. Chevrolet created the Electricus Torque Motor 454 with smaller valves and revised cam timing. They were all chasing what IH had stumbled into, the realization that in endurance racing, average power mattered more than peak power. The 1976 Mexican 1000 became the ultimate validation. It was considered the toughest off-road race in the world. 1,000 miles of the most brutal terrain Mexico could offer. Temperatures reached 118 degrees. Silt beds could swallow a vehicle. Rocky sections could destroy suspensions in seconds. And Malcolm Smith, already a legend on two wheels, decided to enter a four-wheeled vehicle for the first time. His choice? An International Scout with a 345 V8. Not even the big 392, just the smaller 345, making 197 horsepower. His reasoning was simple. "I don't need to go fast," he said. "I need to keep going when everyone else stops." The race started with 247 vehicles. By mile 500, only 89 were still running. Smith's Scout was in 15th overall, but still running perfectly. The engine temperature had never exceeded 195 degrees, despite ambient temps over 115. Oil pressure remained steady at 50 psi, and by mile 750, attrition had promoted Smith to 7th overall. He was now ahead of factory-backed racing teams with budgets 10 times his. His secret? He never pushed the engine. Cruising at 2,500 RPM, the 345 was producing about 140 horsepower continuously. That was enough to maintain 45 mph average speeds while barely stressing the engine. Nenad ET mile 900, with only 100 miles to go, Smith was in 4th place overall. The 3 vehicles ahead were all lightweight buggies with racing engines, but they were struggling. The heat and distance had taken their toll. One was running on 7 cylinders, another was overheating every 20 miles. The third had already gone through 2 fan belts and was nursing a slipping clutch. N. Smith passed all 3 in the final 50 miles. He won overall. A stock 345 V8 making 197 horsepower had beaten purpose-built race vehicles with twice the power. His engine used 47 gallons of fuel. The second-place buggy with a racing small block used 78 gallons. The IH engine had won by being more efficient, not more powerful. And the victory sent shockwaves through the racing community. How could an engine designed for harvesting corn dominate racing? The answer lay in a fundamental misunderstanding of what endurance racing actually demanded. Racing had always been about maximum performance, higher RPM, more horsepower, lighter components. But endurance racing wasn't about maximum anything, it was about optimum. The optimum temperature for sustained operation, the optimum RPM for fuel efficiency, the optimum torque for maintaining momentum. NIH engines were optimized for exactly these parameters, just in a different context. A combine harvesting wheat operates under full load for hours at a time. It needs to maintain constant ground speed regardless of crop density. It can't afford breakdowns during harvest season. These requirements accidentally created the perfect endurance racing engine. But here's where it gets even more interesting. In 1977, emissions regulations forced International Harvester to redesign their engines. The new oiled smokeless combustion chambers reduced emissions but also narrowed the torque curve. Peak torque now occurred at 2,400 RPM instead of 2,000. The torque spread where the engine made 90% or more shrank from 2,300 RPM to 1,800 RPM. NHNO racers immediately noticed the difference. The 1977 engines were actually more powerful. The 392 now made 245 horsepower. But they were less successful in racing. The narrower torque curve meant more shifting. The higher torque peak meant the engines had to work harder. Reliability suffered. Performance dropped. A back-to-back test at the 1978 Riverside Off-Road Grand Prix proved the point. 2 identical Scouts, one with a 1976 engine, one with a 1978 engine. The 1978 engine was faster on the straights, but the 1976 engine was faster overall. The driver of the 1976 powered Scout completed 47 laps. The 1978 version completed 44 laps before overheating, and this highlighted something crucial about engine design. Specifications don't tell the whole story. The shape of the power curve matters more than the peak numbers. An engine that makes 300 lb-ft from 1,500 to 3,500 RPM is more useful than one making 350 lb-ft at exactly 4,000 RPM. International Harvester never fully capitalized on their racing success. By 1980, the company was in financial trouble, eventually selling their Scout line to focus on commercial trucks. But their engines had proven something important. The legacy lives on in unexpected ways. Today's most successful endurance racing engines follow IH's template. The diesel engines dominating Le Mans make moderate power over broad RPM ranges. Trophy trucks in Baja run big block engines with mild cams and conservative tuning. The focus has shifted from peak power to area under the curve. Oil and modern engine management systems try to replicate what IH did mechanically. Variable valve timing broadens torque curves. Direct injection improves low RPM combustion. Turbocharging fills in torque holes. But these are complex solutions to a problem IH solved with simple, overbuilt components. And its end of the engineering philosophy extends beyond racing. Modern truck engines prioritize torque curve shape over peak numbers. The Ford 7.3-liter Retar's Godzilla V8 makes 90% of peak torque from 1,500 to 4,500 RPM. The GM 6.6-liter L8T maintains torque from idle to 4,000 RPM. They're all chasing what IH perfected in 1961, constant, unwavering pulling power. On and in, there's a lesson here about engineering assumptions. IH engineers weren't trying to revolutionize racing. They were solving agricultural problems. But those solutions accidentally addressed racing challenges nobody else was considering. While others focused on going faster, IH focused on never slowing down. Then the International Harvester racing engines remind us that innovation doesn't always mean complexity. Sometimes the best solution is the simplest one. Build it heavy, make it reliable. Give it a torque curve flatter than Kansas. Then watch it embarrass purpose-built race engines by simply refusing to quit. On trend today, surviving IH racing engines are coveted by collectors. A Strape-prepared 392 can sell for $15,000. Original Mexican 1000 winning Scouts trade for six figures. But enthusiasts aren't buying them for their historical significance alone. They're still using them. Nenin, vintage off-road racing, IH-powered vehicles remain competitive. 50-year-old engines still finishing races, still climbing Pikes Peak, still churning through Baja silt. They're not the fastest. They never were. But they're still running when others have long since expired. The ultimate irony. International Harvester's greatest racing engines were never designed for racing at all. They were designed to harvest grain, pull plows, and operate irrigation pumps. Their racing dominance was an accident, a byproduct of agricultural engineering requirements that happened to align perfectly with endurance racing demands. Lant and modern engineers study these engines trying to understand their durability. They analyze the metallurgy, the clearances, the combustion chamber designs, but they often miss the fundamental philosophy. These engines were built to work, not to impress. Every component was designed for decades of operation, not seconds on a drag strip. In an age of 1,000 horsepower supercars and 9,000 RPM sport bikes, the IH racing engines seem quaint. But horsepower is easy, reliability is hard. Making power for 10 seconds is simple. Making it for 10 hours is engineering. The next time you see a classic International Scout or Travelall, remember what lies under that hood. It might not look like much, just a dirty agricultural-grade lump of iron. But that engine was bred from the same philosophy that conquered Baja, dominated Pikes Peak, and proved that sometimes slow and steady really does win the race. These engines changed how we think about performance. They proved that torque matters more than horsepower, that efficiency beats power, that reliability trumps speed, that sometimes the best racing engine is one that was never meant to race at all. What's the most unexpected racing success you've ever witnessed? Drop a comment below and share your story. If you enjoyed this deep dive into International Harvester's unlikely racing dominance, hit that subscribe button for more stories of engineering underdogs that changed the game. Until next time, remember, it's not about how fast you go, it's about how long you can keep going.